Welcome to The Quantum State, a podcast exploring the latest research and innovation in quantum computing. Join us as we dive into groundbreaking breakthroughs, trends, and news shaping the quantum landscape. Discover the cutting-edge developments pushing the boundaries of computing technology. Through insightful discussions, expert interviews, and in-depth analysis, we unravel the intricate theories and real-world applications driving this transformative field. The Quantum State also offers updates from BTQ, sharing the company's research progress and innovative products at the forefront of quantum computing. So, embark on this mind-bending journey with us as we navigate the realm of quantum computing, witnessing its potential to revolutionize our world. Hello, everyone, and welcome back to The Quantum State. I'm Anastasia Marchenkova, and I'm here with my co-hosts, Peter Rohde and Gavin Brennen. It's nice to be back. So the last roundtable episode, we talked about the threats of quantum computers to encryption and some mitigation strategies that could protect this modern-day encryption from the quantum threat. So today, we really want to talk about how far away are we from this being a reality in the hardware side. So to kick off, maybe we can start with a basic rundown of what qubits are and why they're crucial for quantum computing.
Well, a qubit is really an abstract concept. It's not something physical as defined. Like it refers to anything in a quantum context where you have two distinct levels that you can control. Just like a classical bit isn't necessarily an electronic signal. It's more generically anything that can have two binary values. It could be a marble or whatever. And then under that umbrella, you get all of the different ways you could physically go about implementing that. And that's where the huge diversity of different physical platforms comes from, and all of the respective difficulties associated with how hard is it to do entangling gates or single qubit gates, and how long do the lifetimes of the qubits last?
Yeah, that's the funny thing when we're explaining qubits. We have this block sphere that we talk about, right? And it's a very abstract mathematical concept. And then the question beyond that is, wait, but actually, what is it? You know, what can it actually be in the hardware? So what are those broad categories of quantum hardware? We have some common ones: superconducting qubits, trapped ions, neutral atoms, photonics, topological qubits.
Yeah, that's right. So it's just to add on the qubit part, like oftentimes in classical computing, you think of bits as just an abstract notion. You don't actually think about the physics of what encodes a bit, although there are, actual physics associated with that. And something that's really been transformative in quantum technologies is recognizing that this important principle that information is fundamentally physical. It's subject to the rules of our universe, and those rules include quantum mechanics. And so the physics of the qubit is absolutely inextricably linked to how it behaves. And so in terms of these broad categories of quantum hardware, I think the ones you mentioned are generally viewed as the biggest contenders. There are some others like floating electrons and liquid helium. Topological qubits haven't actually been demonstrated yet. The theory is quite exciting because they offer the potential of much longer resilience times than the others, but it's still not seen yet. The big contenders are certainly superconducting, trapped ions, neutral atoms, photonics, and they all have different advantages and different advantages.
Yeah, it's kind of the tough thing right now. The big question we get is, which one's the best quantum computer, right? We're all kind of like, we're still so early. They all work so differently. And I think an exciting thing with this year of the quantum technology is we started seeing that different types of hardware may be useful for different problems or have a little bit better performance in certain problems. So that's been really interesting to see finally coming out in real life. So first, let's cover some of these hardware modalities. And first one, superconducting qubits. What are they and how do they work?
So in superconducting qubits, which is not my field of research, so don't quote anything I say whatsoever. But coming back to what are the two levels, that's what it's all about. And in superconductor, you can have current flow, and the current flow just goes on forever without resistance in a superconductor. So you imagine current flowing around in a circle. It could go either direction, but in a quantum context, it can actually be a superposition of those two. You can have current going this way and that way at the same time. And there you've got your two levels that you can use to encode a qubit. That, of course, comes with additional challenges. How do we make those interact with each other to do gate operations that we need? And that's, of course, where it becomes very, very tricky. But as you can guess, superconducting qubits, because they're superconducting, there's a whole lot of hardware that's quite challenging. You need very, very low temperatures to achieve superconductivity. And it's both expensive and introduces all sorts of spatial constraints. So just like all of the other platforms, it comes with many, many challenges.
Yeah, this one is the one I refer to as the classic quantum computer, because that's the one you see in all the press releases, because it's that steampunk chandelier that you see. And that's actually not the quantum computer. That's just the dilution fridge that holds the chip inside and actually does all the cooling. Like you mentioned, there's a lot of peripheral hardware that we need to cool it down to low temperatures. So this chip has to be at 10 millikelvin or below to really function well. There's a lot of different operations that have to be done, a lot of wiring that has to go through that, controlled by RF pulses. There's a few new technologies kind of coming in to handle the scaling problem. But one of the big things I say with superconducting, because I've worked in these for a little bit of time now, is they are kind of not, I mean, they're not natural qubits. We've created them, right? So that's something a little different than the other modalities that we're going to talk about. So for example, the next one, let's talk a little bit about trapped ions and how they work and what they're used for in quantum computing.
Yeah, so I was studying trapped ions when I first started my graduate work, and I visited Dave Wineland's lab even before he received his Nobel Prize. So it was really special visiting there, because just the amount of attention they put to these systems was incredible. Lots of decades of research. But what's interesting about the trapped ions is it's a qubit, which is the same everywhere in the universe. So, the atom is a sort of a self-organized structure, and they store the qubits in the electronic state of the valence electron. So they basically take one of the elements from the second column in the periodic table, kick off an electron, and then you have one valence electron, and that acts as a charged qubit. And so this one is in many ways a natural qubit, because it is used in technology already that has the highest precision of anything performed by humans. So we can measure frequencies based upon the oscillation frequencies of trapped ions with better precision than anything else we can measure. So it has very long coherence times and extremely precisely known transition frequencies. And the idea is that you trap up several of these in electrodynamic traps. And if you just do a string of them, it forms like kind of a self-assembled string. And then you could have a segmented array where you have lots of different zones where trapped ions exist. And then you do gates by coupling the electronic state to the motional states of the ions. And so been tremendous successes with these systems, but they tend to be slower than other systems. They are certainly slower gate speeds than superconducting qubits. And so it's advantages and disadvantages for those.
Yeah, I think that's one of the big things, right? It's so hard to say what's the best because it's so hard to compare, right? You say trapped ions, well, it's great. We don't have to manufacture them. They're perfect by nature. They wouldn't be that ion if they had an issue with them, right? So, but there's that issue with the gate times, right? So you're saying, well, okay, there's a long coherence time, but how many gates can we actually run? And so you start looking at those practical applications, and then things change. So those are kind of the two ones that we've heard a lot about in the last few years. What about photonic architectures? That's an interesting one because there was a lot of hype about it, a lot of funding going into it quite a few years ago. Then it died down for a while, and then I think it's back. So what's the photonic architecture in quantum computing?
Right. So this is the area where I've spent most of my career. And what you just said is interesting. There have been some ups and downs. Initially, there was a huge burst in interest after it was first theoretically described that you can use photons to build a large-scale quantum computer. And here, your two levels that can be implemented in different ways. You can have what's called dual rail encoding, where you have a photon in a superposition of two distinct locations, say two different optical fibers, for example. Or you could also encode in the polarization. That's a very natural one that is automatically there in any photon. Its polarization can define a qubit as well. Now, it got a lot of interest, but then it started stagnating because we realized there are enormous engineering difficulties associated with it. And the primary one is that in any quantum computing architecture, you need feed forward, which means the ability to measure some of the qubits, then use the outcomes from those to decide how to adjust the circuit before the remainder of them go in and undergo further evolution. That's especially necessary for any kind of error correction where you need to extract information about what errors occurred and then make changes. The problem with doing this photonically is that the photons are moving at the speed of light. So you've got all your photons coming along, you need to measure some small number of them, and then before these other ones get to the next part, you have to do some post-processing, decide what to do, go ahead and change the circuit. So you can see that introduces a very difficult problem because it's hard to beat the speed of light. You need to slow things down. So you can use delay lines or quantum memories, and that just introduces a whole bunch of new engineering problems. So that was the holdup. And then this idea of boson sampling came along, which is what many of the headlines have been lately. And this is a simplified and non-universal model for quantum computing where it doesn't require feed forward at all. It's just completely passive. Photons go through a circuit, you measure them at the end, no feed forward whatsoever. And this approach lets you do things that are post-classical, so better than what any supercomputer can do. But unfortunately, it implements a very specific type of problem which doesn't really have a lot of utility and certainly can't fulfill the promise of all the different exciting algorithms that we hear about.
All right, so that's photonics. So that's really interesting because I didn't know about the reason for that. And boson sampling, that reminds me, you all did some work with boson sampling on the proof of work. Is that correct?
That's right. That was some work we did to try and find an actual use case for it. And it turns out that does provide one. We were looking at, Gavin and I and some others were doing some research. Can we do proof of work, which is a concept in blockchains, where this is a mechanism for choosing a random selection of nodes to form consensus on the addition of a transaction? That, as you might have heard from other headlines, is hugely inefficient. You see these headlines about, Bitcoin using the energy of Greenland, and they're not exaggerating, like it's actually true. So trying to make these things more efficient is a pretty important problem to try and address. And so by substituting the conventional classical approach to proof of work with a quantum problem based on boson sampling, we're able to show that you can achieve the same thing with significant energy reduction.
Very cool. Okay, so the next one, we've mentioned it a little bit, and it's very controversial. What are topological qubits, and how do they differ from all of these other modalities?
Yeah, so this is maybe, in my opinion, this is the most fun qubit to learn about, and I still teach it in classes. And it goes back to an idea by Alexei Kitaev back in 1995, where when he came up with his famous surface code idea, which is one of the prominent quantum error correction codes, for example, being used by Google and IBM with their superconducting systems. At the same time, he proposed a way to do quantum computation by just moving around these kind of fake particles called anyons. And we're usually in our normal universe, we're used to particles that are bosons or fermions, depending if they have an integer spin or half integer spin. Electrons, the mass carriers are fermions, and the force carriers are bosons. Light is a boson. But he came up with this new way to get an enyon, which acts very differently. And all you need to do is just wind one enyon around another, and that performs a logical gate. And it has a lot of resilience to noise in your system. So it seemed like almost a magical idea. And then later, he and others showed how you could actually engineer systems which would allow you to create excitations on them just using, kind of electric pulses and applying different fields and move them around. And so people got very excited about this. In particular, Microsoft Research devoted over a decade-long program to work on topological qubits in using nanowires. And so they invested quite a bit of resources. They brought in a Fields medalist in mathematics who was, did work in topology, Michael Friedman, as well as many other notable physicists and experimentalists and theoreticians. And they've been working on this, but still have not seen the topological qubits. They're referred to as Majorana edge modes. They're like particles that live on the edges of these nanowires. And they just have not actually found definitive evidence of these anyons. So in my opinion, if they did show it, that would be a Nobel Prize winning research discovery. But at this point, I would say it's lower down the chain of what are considered feasible architectures for quantum computing.
Yeah, I think it was, what year was it? There was a year that Microsoft announced that they'd actually created this and were able to, I don't remember if they said they were able to do a gate, and then that was retracted a few months later. That was, right. What year was that, 2018?
Yeah, around there, yeah.
Something like that. But then they have said in the last couple of years, they are still committed to the topological qubit approach. They're continuing research down that path.
Yes. Yeah, I would say I hope they have a plan B.
So you don't put any trust in the Majorana existing?
There's a lot less enthusiasm in the field than there used to be. Yeah, I got to say. Yeah, it's a hard problem. No question. There's fantastic people working on it, but it's a lot harder than people expected.
Yeah, I think it's an interesting one because it has a lot more, in superconducting the trapped ions, research has been going on for a while. Manufacturing has been going on for a while. We know kind of what the problems that we're going to hit are, right? We're talking about the 1,000 qubit. We know the scaling for the Creo stuff is going to be kind of a tough problem to solve. People are already trying to figure out, like, how do we kind of build a Creo set large enough to hold this? How do we reduce the wiring and everything like that? It's kind of a known issue. And here there's just a lot of unknowns about if that's going to be possible. And then how do you scale it up and a lot of other factors. But again, because like you mentioned in the theoretical end, there's a lot of benefits to that. If that manages to be overcome, there might be less problems on the other side of it.
Right.
Okay, so we talked a little bit about this, but what limitations, disadvantages should we be aware of with any of these systems? What should we really look for in, let's say, like a good qubit or a good system? What do you all look at?
Well, there are many, many, many different ways you might quantify that, because there are quite a number of things you need to simultaneously work and work well if you're going to make a scalable architecture and build a large-scale quantum computer. So you need not just qubits, but you need the ability to do single qubit gates on them, and you need the ability to do entangling 2-qubit gates on them. And the performance of different architectures in those two contexts varies enormously. For example, in optics, which I mentioned, single qubit gates are really trivial. If you want to do a single qubit gate with a polarization encoded qubit, you just use a device called a wave plate, which rotates polarization. And it's very easy and simple to do with very, very good quality. But the disadvantage is that when you try to do entangling gates between qubits, it becomes very, very tricky. There are other architectures where things are very much a different way around, where it's much more practical to do entangling qubits, but there might be other issues. Photons, for example, are subject to loss as a dominant source of error, whereas in other architectures, things don't get lost so easy, but they might undergo other forms of noise from environmental interaction. So it would be a mistake to ever think of things in terms of is one particular architecture better than another. It's always with respect to a whole bunch of different criteria, and none of them are superior at all of them simultaneously, which is the reason that we're still pursuing all of them simultaneously, because we just don't know.
I was just going to add that it's interesting if you look at the metrics that the companies focus on in their press releases. Some companies like IBM talk about quantum volume, which is sort of a measure of how many gates you can do over some number of qubits. Others will publicize the gate fidelities. So basically, what's the error per gate? And then others will just talk about the number of qubits they can control. And those are all good metrics. I think probably the most important metrics are like certainly error per gate and some demonstration of how you can scale up. So you might have some systems that work very well for maybe 50 to 100 qubits. But if you're going to get to the level of having hundreds of thousands, millions of qubits necessary when you include error correction overheads, then that architecture may or may not appropriately scale up. And certainly the superconducting people have been talking about this a lot recently. And one other metric I just wanted to talk about is I went to a couple conferences just over the past 2 weeks on the role of energy in quantum computation. So you don't often hear so much about the energy cost of running quantum computers. Usually people talk about the time or the number of qubits. But more and more researchers and companies now are starting to talk about energy advantage you would get by running their devices versus classical computing devices. And we'll probably soon start to hear about companies arguing their quantum architecture is better than other quantum architectures in terms of energy costs.
Yeah, that's really interesting. Yeah, I think we were all at a bunch of end of the year conferences this week, and it's interesting to hear the hallway conversations because, like you mentioned, there's quantum volume. IBM uses it because IBM created it, right? So there's also a little bit like, they're looking at, maybe they're looking at parameters that their computers might be better at, but there's also algorithmic qubits, also by IonQ. So again, this is a company putting out a metric that hopefully they will look good in. Otherwise, why would they put out the metric? But I think one of the things is, I worked a little bit more on the application specific side. So our chips looked bad compared to others because they didn't have all-to-all connectivity, and some of these metrics looked into that as a parameter. So I have a joke that I tell to everyone, which is like, I can give you 1 million qubits right now. You won't like them. They're not going to be doing anything, right? So in the end, like this is a very difficult problem that we have to try and figure that out. And one of the things I saw at this conference that I went to, I was at Q2B in Santa Clara, was all the hallway conversations that I had were, we'd said years ago that certain modalities are going to be better for certain types of problems. And like Peter, you said that we're pursuing all of them because we still don't know which ones are going to hit certain things. We seem to know that certain problems are going to be better on certain types of hardware, but we still don't know how they're going to scale in the long term. I saw at this conference that was really starting to come out. So I was hearing somewhere in the background that people were running ML algorithms, and they seem to say that trapped ions are they're getting better result on trapped ion systems in the machine learning space. However, going back to superconducting, certain algorithms only need a linear chain type of architecture system, and we are seeing better results on those because you don't have to build all those extra connections. But that chip would look worse on those metrics, even though it would perform better for that specific algorithm, which is, again, why this is so difficult for us to kind of say which quantum computer is best.
Well, it also leads to the ultimate definition of a metric, which is what problem of practical interest can it solve?
Yeah, definitely. I think that's what we're waiting for. I was talking to some folks again at the conference, and it seems sometimes what is quantum advantage, right? What is a quantum computer? That definition shifts depending on where you are in creating your quantum computer. Is it one that just has qubits? Is it one that has a certain error rate? Is it one that can solve a problem that has an advantage, even though that problem is completely useless? Are we waiting for the first application for a real problem, or are we waiting for one where it would save the company money? So there's a huge range of what we can consider, I think, the first quantum computer. So we can say everyone can have the first quantum computer depending on their definition. All right, so now that we've talked about that, and I've talked extensively about how qubits don't matter, I'm going to ask, how many qubits do we currently have?
Well, let's see. IBM announced their 1,000-qubit device, but I don't know if it's all connected. Do you know?
So I don't know what the connectivity of it is either, but perhaps the question needs to be also qualified with what kind of qubit, because not all qubits are equal. There is this distinction between a physical qubit, which is the one that you actually build in a two-level quantum system, and a more abstract logical qubit, which is one that represents information used in the computation. If you have no errors, they can be the same thing. But once you add error correcting codes, they become very different, and there's some multiplier between them. These days, if you answer the question, how many physical qubits do we have? Well, the number is highly variable, but more to the point, for those that are making the claims of the largest number of physical qubits, what does that translate to in terms of logical qubits? And the answer is we don't really have robust logical qubits at all in any of the architectures, at least not in a reproducible kind of way. There have been demonstrations of very small scale error-corrected qubits making relatively low noise logical qubits, but we just have this huge gap now where everybody's talking about physical qubits, and everybody's definition of a physical qubit is completely different because they can be quantified by different measures.
So there was a quite important announcement that came out this month, published in Nature by the Harvard group in collaboration with the company QEra, who does neutral atom quantum computing. And they announced the full control of 280 physical trapped neutral atoms in optical tweezer arrays, where they encoded 40 logical qubits using something called color codes. They're very similar to surface codes, which is a commonly used code. And they also demonstrated 48 logical controlled control Z operations. That's very technical language, but it's a particular operation which is generally seen to be a hard operation because it involves interactions between three particles, and in this case, it was 3 logical qubits. So that was quite a significant announcement. And I think we're going to hear a lot more from neutral atoms in the coming days, years.
Yeah, I've heard there were a lot of hallway conversations at Q2B about neutral atoms. There's a couple companies in the space and doing some impressive things. So yeah, they announced that. It was actually funny because Q2B, usually Preskill and Aronson go at the end, and they kind of talk about like, oh, quantum computers really haven't done anything lately. We're still so far away. They, for some reason, were first, I'm sure due to travel schedules or something. And they did that. And then the next day, QEra announced the 48 logical qubits system the next day, and everyone was like, oh, maybe we should have aligned on that. But yeah, that was funny. I think that was a huge leap. I haven't read the full paper yet, but yeah, neutral atoms are kind of trapped ions were kind of always considered better as a system, but neutral atoms seem to be catching up to the trapped ion, and more and more companies are being formed around that.
Yeah.
So,
yeah, they so I actually did my PhD work on trapped atom quantum computing, and there we looked at optical lattices, but the more recent technology uses optical tweezers, but it's still trapping them in light. What they use what are called Rydberg states, which are highly excited states of the atoms, and they can get fairly good gate speeds. Maybe not as good as superconducting, but still, several megahertz. They have the advantage again that it's the qubit is the same everywhere. You don't have to manufacture the qubits, and you can get lots of them trapped. The measurements are still a little bit tricky. Like, for example, it's very hard to get three-dimensional arrays of these things. They tend to work in 2D arrays, or maybe just a few stacked 2D planes. But right now they work by moving the qubits around to do operations, and this ability to move the qubits by basically just aligning how the tweezers are oriented. They can do gates which allow you to use codes which are more efficient than surface codes. So that's one of the exciting things when people are pushing to use things called low-density parity check codes. Same kind of codes we use in cell phones for classical encoding. There's quantum versions of these things, and neutral atoms seem to be a good architecture for those codes.
You mentioned a little bit about the 3D arrays, but I think 3D arrays have been kind of tough for everyone. Is that correct?
Well, that's true. Yeah. Yeah.
I remember something like 2015, there was a lot of people trying to pursue the 3D arrays for scaling, and I think that's also died down a little bit over time.
Yeah.
All right, so now that we've talked about how many qubits we currently have, and very good point here on logical and physical qubits, that's always been my play, right? Because there's papers that use logical qubits or physical qubits. They don't specify that. That's a lot of confusion. So how many qubits do we need for breaking encryption?
Oh, that's a good question. People have done this explicit calculation. In fact, I think Gavin has.
Yeah, and people have done much better calculations than I have quite recently using more advanced codes. And really one of the exciting results I saw from earlier this year was by researchers from the company Alice and Bob, who showed that using a particular kind of encoded qubit called a cat qubit. It's referred to as a cat qubit because it goes back to the idea of Schrodinger's cat, where you'd have a cat in a superposition of alive and dead. The cat qubit is a superposition of having like a mode be in one place or another place. And usually when we say mode, this is like a light mode or a microwave mode. These things are routinely controlled in experiments, and many companies have access to these cat qubits now, and particularly in superconducting systems. And so what they showed is that you can crack elliptic curve cryptography with 256 bits using around 126,000 of these cat qubits. So why this particular problem of 256-bit elliptic curve cryptography is interesting is that it happens to be the cryptography that's used, for example, for digital signatures in Bitcoin, as just one example. Many other applications as well. But this would be a huge thing. In fact, this would be clearly disruptive to the economy of the world if such a computer were devised, because you could run such a computer in, I think they estimated something like 8 hours to be able to crack it. And this is one of those problems where, as far as we know, there really is an exponential gap, that the best classical algorithms known to crack elliptic curve cryptography scale exponentially with the bit length. So this would be a tremendous feat. And I'm sure the security agencies took notice of this result. And we'll see how the technologies develop with these cat qubits. They made some assumptions on connectivity of the architecture and the noise model, but I consider that a really big result.
Definitely, it's a huge result. I actually got to talk to the founder at Q2B. They were there as well. So I definitely approached their booth and was like, I talked so much about you all in the videos. This is really exciting because, yeah, a lot of people still cite, Preskill's old documents saying 10 million qubits, right? And that was, I think, 2014, the lecture that I kind of refer to where he talked about last. 2 orders of magnitude improvement in less than a decade is huge. If we're going to get another order or 2 in the next decade, systems are going to be a little bit threatened by this. So how has this number of qubits that we have seen in experimental quantum computers changed over the last few years? And what kind of milestones are we looking for in these systems where we're going to start either worrying about encryption or certain types of applications?
I think that the point at which everybody will really take notice is when someone demonstrates that in a reproducible way they could make logical qubits, in other words, ones that are individually error corrected against what all of the underlying physical processes are. And if you can do that and demonstrate that it's reproducible and that those qubits are able to interact with one another, that's really the turning point where we shift away from all of this near-term intermediate scale stuff that we hear a lot about, like boson sampling and all these different other sorts of quantum sampling problems that solve contrived problems. That would be the transition point where we start switching to something that really poses a long-term threat. But the answer to how long that will take is as diverse as the answer to the question on what's a qubit, because for every choice of qubit, you get a very different answer to these questions and what the fundamental limitations in scalability are.
Oh, so by the way, there's a website called Manifold where you can bet on future events, and I posted a question on there on what will be the first quantum computing architecture to crack 256-bit elliptic curve cryptography. And I put the close date as December 31st, 2033. So I guess you could say that that's a little bit of a prediction from myself that it will be clear which architecture will do that by that point.
It's interesting. What are the results so far?
Well, right now, neutral atoms are ahead. But
really?
I have photonics on there, superconducting, trapped ions, and yeah, that's it. I included actually both discrete variable photonics for like what PsiQuantum is doing, and also continuous variable like what Xanadu is doing.
I'm actually a little surprised neutral atoms are kind of first. I wonder if that's related to kind of atom computing's announcements lately. I've seen a lot more chatter about neutral atoms since that came out.
Yeah. Well, also there's not a lot of votes yet, so that's why I only discovered this site recently. So
you need to send it over. We'll tweet about it and get more results.
Great.
Okay, so going back to the quantum supremacy side of it, what are we looking for on the qubit count to hit this milestone?
Well, you could argue we've already hit the quantum supremacy milestone. It's just that it's only for a particular, very restricted and not very useful class of problems. So the question of have we achieved quantum supremacy, it appears quite convincingly that the answer is yes. It's just that it doesn't do anything that anyone really cares about so much. When the same thing happens, but it's a problem that people care about, then it becomes a different story. And there, well, what is the number of qubits you need? Well, that again also depends on what type of problem you're solving and how big the instance of the problem is. It's not as though all elliptic curve problems are the same problem. You can have different size key lengths. All of these things scale, and they scale equivalently the size of the quantum computer that you need. But we've certainly reached the benchmark already. It's just that we'd like to reach it again, this time for something more useful.
Yeah, it's of course the question of what is useful is very interesting. So, there are some estimates that with around 1,000 or so physical qubits, you could perform a calculation for a Fermi-Hubbard model, which is a particular model studied in physics that's just electrons hopping on a surface with some interactions. And it turns out this is a problem that's very hard to do with classical computers. It does get worse as you grow. It gets exponentially harder with the number of electrons you have in your system. And so there are estimates that with like on the order of 1,000 or around there, you could do something that would be very difficult for a classical computer. Or maybe out of reach entirely. But that's maybe not so useful for most of industry, at least not directly. So yeah, in terms of more maybe industry relevance problems, a lot of focus has been on optimization problems. Everything like the knapsack problem, which goes back to just like what's the most value you can get by adding items to a knapsack where there's some weight to each item. So you can only carry a limited amount of weight, but you want to get the most value. That's a very simple problem, but something that shows up all the time in, certainly the military cares about it, and anything where you have some supply chain issues. There it still looks like if you want to do things fault tolerantly, it's going to be difficult. There are some claims from companies that you can use annealing or non-error corrected computing, but I haven't seen any convincing arguments that those approaches would be able to see an advantage that you couldn't get with classical computers given the same investments. Of course, you can throw millions into a quantum annealing device and say it does better, but then you could have invested the same millions into just a bunch of NVIDIA machines. So I still am somewhat skeptical of near-term quantum advantage for industry relevant problems. I hope I'm wrong, but I just haven't seen it yet.
Have you all seen, this is kind of an aside, but I was poking around on Twitter, and is IBM not allowed to use NISQ anymore? NISQ is noisy intermediate scale quantum devices. Have you all seen that?
No, I haven't seen that, but I can understand why they would do that.
Why do you think?
Well, it's been thrown around so much by companies that are just selling a dream. They're pretending like they're going to get these quantum advantages, significant advantages from non-error corrected devices, and they don't have any solid theoretical arguments for it. And the experiments, I would say, are not convincing about scaling up.
All right, so now let's talk a little bit more about, apart from qubit count, what other parameters are essential for assessing the performance of a quantum computer? So we talked a little bit about that on the qubit side, but what are the factors you look into when evaluating these experiments and saying they're convincing or not?
Well, suppose you had an algorithm that required a certain number of logical qubits, so error-corrected ones, to implement a certain algorithm of interest. Now, the first thing that feeds into answering the question is what is the type of qubit, because they have all different types of noise models and noise rates, which is not even just a single rate. It can be dependent upon what you're doing. Like a single qubit gate, typically in many architectures, will have a lot less noise than a 2-qubit gate. So you end up with all sorts of different parameters within the architecture. Then there are the constraints on how they can interact with one another, the connectivity. All of that feeds into answering the question of what's the right way to error protect this, because different connectivities and different types of noise, they all guide you towards choosing different types of error correcting codes to, in the best possible way, overcome those errors. So all of those different factors feed in. And then ultimately that results in a decision of what the whole error protection architecture is. That gives you an idea of how many real qubits, physical qubits, the whole thing is going to require. And this is a quote from a colleague, Simon Devitt. I think it's his quote. He said, the vast majority of any quantum computer is not doing quantum computation at all. It's just correcting its own errors. So the bulk of any architecture in the future is just trying to remove errors themselves. So at the end of all of that, then you've got, well, what's the depth of the circuit? We've got all of this error-protected architecture. How many rounds of gates do we need to actually implement something useful after that? And then depending upon the type of qubit and the lifetimes and whether you can do feed-forward or not, that will affect that calculation enormously. So the answer at the end of all of that is that the variance stretches all the way from one side of your arms to the other, and you can't put a pin on anything unless you know all of those contributing factors.
So yeah, I think some other parameters to pay attention to are error correction clock cycle times. So you might even have an architecture which has a fast elementary gate speed. That is the time it takes to do a single qubit gate or a 2-qubit gate. But really what's important is the time to do a whole error correction clock cycle. You have to do these all the time, like Peter was saying. Even if you're doing nothing, you have to continually doing these error correction clock cycles. So that's a number. Certainly the gate fidelities. What's the error per gate? Because that'll tell you something about the overhead you need for error correction. And I think energy is also an interesting new metric to consider. What's the power requirements? In superconducting, you need cryocoolers. Also for photonic systems, you're going to need them for the detection. For atomic systems, you need lasers. So there's a power associated with that. And then there'll be an overall time to run your computation. And from that, you can extract an energy.
Yeah, so I want to dive deeper into that. What is the energy cost to run quantum computation on these systems? Are you looking that more dollars worth? Are you looking, how are you kind of measuring this? And what is the right now?
Oh, right. So yeah, I know it was a big question. People were wondering, are you going to need something like the size of CERN to do a big quantum computation? Because then, all right, great, you have the super fast computer, but you're also going to deplete a huge amount of the world's energy. And so there was actually a nice analysis done that was led by Alexis Affez in Grenoble by a team there. And they looked at estimating the energy cost to crack RSA 2048 using superconducting quantum computers. And they estimated something in like I believe it was the 4 megawatt range of power. And then, of course, then you'd multiply it times the time to do the whole computation, which I believe is it's like a dozen hours. Now, of course, that's going to completely blow away anything you could do with a classical computer because you get this super polynomial speed up. But it's nice that they put some hard numbers on that, because then you could translate that into other problems, like, for example, quantum chemistry. If you know that that's kind of the power requirements, then you can make a good judgment. is this really something that's going to be cost effective for companies to pursue? And I think I took their result as quite an optimistic one. Actually, I was a little worried that the power requirements might be much worse, but they seem to show that actually it's not so bad.
Yeah, that's a really good point, because we see in these pitches for quantum chemistry that even if you can save 10 to 20% of their development time or budget, that's $1 to $2 billion. The quantum computer itself is not going to cost that much. I mean, it's still an expensive piece of hardware, but it's not billions of dollars of hardware. But if the power requirements are too high, then they're just not going to use it, right? Depending on the speed up. So then the question becomes, is it time to market that's important? But again, then if the costs are too high, nobody's going to do it, and it's just going to kind of disappear.
Yeah, and I mean, 4 megawatts is still a lot, but they estimate if you go to better error correction codes, you could get down to tens of kilowatts.
All right, so now that we've talked about where we are in the hardware, what we're looking for, what should we expect in quantum hardware developments within the next 5 or 10 years?
I think one thing that we will start seeing in the next 5 to 10 years is announcements of exactly what we were talking about before, of logical qubits being developed, regardless of how scalable it might be. People are certainly thinking in that direction and realize that's what's necessary to move the field forward. I think interest in all of these NISQ era intermediate models is going to start losing attention because people realize, okay, it's not as exciting as maybe we thought. And the really interesting and exciting announcements will be the architectures where they say we've made a logical qubit that error protects itself using an encoding with this many physical qubits, and we've done it in an architecture that in principle lends itself to putting many of them in parallel and scaling it up. And that seems like an inevitable development that will be made and has to be made.
Yeah, and I'm really wondering when we're going to reach the point where it just goes silent, or it just becomes very secretive. I don't know when that's going to happen. Right now, the companies, they seem to be fairly open. I mean, with limits, but at some point, it's going to become quiet. I think we won't know what's going on.
That's how we know something big is happening, and we should be worried about our Bitcoin, right?
Right.
All right. Well, thank you so much, Peter, Gavin. Amazing episode. There's still a lot of questions to ask. We didn't even get into the person that claimed to have cracked RSA 2048 on this episode. So thank you all for listening to the Quantum State. Stay tuned for the next episodes, because I definitely want to ask you all about that. And make sure to like this video. If you're on YouTube, you can comment down below, or listen to this on Spotify or wherever you can get your podcasts. And see you next time.